So good morning, everyone. Today I'm thrilled to introduce to you my final year project, which is the deployment of the rapid control prototyping technique on a three-phase inverter. And the image on the right side of this slide shows the dual inverter prototype, which I've built over the course of the last 6 months. And over the next 15 minutes, I'll briefly explain to you different parts of this project. And I'll start with an introduction of a comparison between the grid following and grid forming inverter before moving on to the background bit of this project, where there are three main concepts I would like to cover, namely the inverter hardware, its dynamics and plant equations, as well as its control. And after talking about that, I will briefly describe or give an overview of the system before I walk through the rationale as well as results I've obtained from various tests. So a grid forming inverter is an inverter that tracks the grid voltage and frequency reference regardless of DC bus voltage or load variations. And when I say following a grid voltage, I mean following the real voltage reference VD, imaginary voltage reference VQ, as well as the frequency reference F. And a good example of this is an uninterruptible supply, which is a DC source applying to an isolated AC network. And the reason a grid-forming inverter is necessary in this scenario is because there are no synchronous generation in the network. So this necessitates the need for an inverter-based resource to actually form the voltage reference of the grid itself. In contrast, a grid-following inverter tracks a current reference and controls the power exchange, namely the real and the reactive, or the P and Q power exchange. An example of this is when we connect a renewable energy source such as a photovoltaic solar panel farm, a wind farm, a wind turbine farm, or other sorts of energy storage solutions to an AC grid where there is already quite a bit of synchronous generation, which determines its actual operating voltage reference. So on the bottom of the slide, I've shown the control diagrams for both in operating modes. And it is important to recognize that we can easily switch between these modes without actual change in hardware, but we just actually need to change the control scheme required. So moving on to the hardware, there are three main parts of the inverter system, namely the three-phase half bridge, which converts the DC voltage to a three-phase AC, an LCL filter, which suppresses the current ripple, as well as a common mode choke, which is not shown on this diagram, but it helps basically reduce the change in common mode voltage, which is the difference between the capacitor neutral as well as a DC ground on this diagram. But before I move on to actually analyzing the plant equations of this diagram, I thought it would be useful to give a brief introduction or a brief refresher on what reference frames are in a three-phase system. So typically we represent things in an ABC frame where we have three sinusoidal and time varying quantities in a stationary frame. But if we transform it into a DQ or synchronous reference frames, this effectively transforms it into two DC orthogonal quantities in a rotating orthogonal frame. And this is advantageous for two main reasons. Firstly, it is much easier to generate a reference signal which is DC, and it is also much easier to have a controller which follows a DC reference signal. And secondly, in contrast to having three coupled signals, we now have only two coupled signals, and as I'll later demonstrate, we can decouple them using cross decoupling gains quite easily. So this brings us to the plant equations of the inverter, and I'd like to note that the plant equations of this inverter are based on an LC filter because the feedback voltage taken is at the capacitor voltage and the feedback current is the inductor current. So this is basically just an LC filter. So the two sets of equations on this slide are the inductor current dynamics as well as the capacitor voltage dynamics. And they're shown in both the space vector forms and also in the DQ forms. And as you can see, when we transform it from the space vector form to the DQ form, there is some coupling between the T and Q axes. That is, we can see the IQ term within the ID equation and also the IQ term within the ID equation. So this necessitates some sort of cross decoupling mechanism, which I'll explain later. So having discussed both how a grid following and a grid forming inverter, as well as the basic rationale of control in the DQ frame, I'd like to discuss the control of an inverter, first for a GFL and then for a GFM inverter. So for a GFL inverter, the aim is to control the power exchange. And since the inverter is a current controlled device as dictated by a plant model we previously devised, we need to first convert the power reference to a current reference as shown by the equations on this page. And in order to in order to control the currents in the DQ domain, we will need a phase lock loop such that the DQ frame of the ABC to DQ transformation blocks is aligned to that of the grid. So that means that the angular velocity omega as well as the phase rho should be aligned with that of the grid. So as you can see on the phase lock loop control diagram here, there's a PI controller which takes in the Q components of VC and corrects it to 0, a filter which attenuates any further higher harmonics, and a voltage controlled oscillator or VCO which generates a phase centered at 50 Hertz based on that error. And in combination, this ensures that the DQ frame rotates in sync with the grid, and this ensures that the D and Q components are indeed DC when the three phases are balanced with each other. So having converted the current quantities from ABC to DQ, we can then compensate the error by comparing it against the reference values, passing it into a PI controller, and applying the cross decoupling mechanism by multiplying it with a cross decoupling gain omega 0 L as shown on this diagram. And finally, we need to convert it back to ABC again because the switches, the three switches will need to be driven by duty cycle separately. And what I've mentioned on the last few slides basically sums up a grid following inverter. And for the next couple of slides, I would like to round up what a grid forming inverter is. So first of all, it has an inner current loop controller, and it has the topology identical to that of the current controller of a GFL inverter, just with different sets of gains. However, there is also a voltage controller on the outer loop of the controller because we want to control the voltage reference of a grid forming inverter. The control scheme for the voltage is shown on the bottom of this slide here, but I'll not go through it in detail because the PI controller as well as the cross decoupling mechanism is quite similar to that of the current controller. So having discussed both a grid following as well as a grid forming inverter, I have decided to summarize the power level diagram as well as the control diagram on this diagram here, which shows both inverters operating in closed loop. That is a grid forming inverter connected to a grid following inverter. So this is the final setup of the dual inverter prototype that we aim to achieve. But throughout the experiments, I've also performed various tests to test the GFL as well as the GFM separately, as shown in this table here. So now I'd like to walk through some of the rationale as well as results for various tests which I've done for this board in order to verify the validity of the model in both simulation and on hardware. So first of all, I performed an open loop test because I needed to check whether the ABC waveforms are sinusoidal and also to ensure that the 0 points of the ABC waveforms are aligned. If one of the things that I checked here is that I wanted to ensure that the amplitude of the ABC waveforms is identical to that of the D reference, provided that there's 0 Q component voltage or current because they are in phase with each other. And this shows that the transform blocks are working as expected. In addition, the fact that the D and Q signals are stable, not that they need to be tracking anything right now, shows that the ABC voltages and currents have a consistent zero point and are properly calibrated. Because any mismatches in the 0 points between the A or B or C phases would have led to a 50 Hz oscillation and led to further instability in the phase lock loop. For a grid following inverter, the aim is to control the power exchange. So I performed a power step change both on simulation and on hardware. As we can see in the comparison between the simulation and the hardware deployment, there is a slight difference in the low frequency angular swing of the controller, and this shows that there is likely a small mismatch in the ESR of the components, and which has likely led to a slight uh, difference in dampening in terms of the simulation versus the hardware response. I've also deployed the experiment with different sets of controller gains on hardware, and when we compare the red line and the green line where we increase both the proportional as well as the integral gains, we can show that increasing those gains leads to a reduced rise and settling time, but it also increases the local oscillations. This is because it reduces the amount of time available for the controller to accumulate the error, which essentially allows it to oscillate more violently. For the grid following inverter, I've also done a very similar set of tests, so I'm not going to walk through them in detail. But having determined the best out of gains from both the grid following as well as the grid following inverter, I've combined those experiments and deployed the final setup on the dual inverter setup. But I had to make 3 key changes. The first change is to reduce integral gains of the inner current loop to increase the separation between the cuts off frequency, which is the frequency at which the magnitude starts sloping, as well as the crossover frequency. So this helps increase the phase margin and the stability of the current loop, which alleviates the bandwidth conflicts in between the current loop as well as the voltage loop. Secondly, I've also increased the integral gain of the voltage controller and also accelerated the PLL response. So both of these changes essentially help reduce the steady state error of the controllers. So in conclusion, for this project, I have successfully demonstrated a dual inverter rapid control prototyping system, which gives a smooth transition from simulation to hardware. And as shown in the results, we can show that the results largely correspond and that the simulation and the hardware are good models for each other. As an evaluation, I've compared it against peer simulation setups as well as setups in high power systems. And in comparison to simulation setups, this setup, it is inherently a hardware setup, which means that it is able to reflect hardware constraints like sampling, discretization, as well as dynamics of parasitics more accurately. So this makes it much more accurate in that regard. But unfortunately, for many renewable energy studies, there's also many other factors which come into play, like solar radiance and also wind power, which affects the DC source quite the DC bus voltage quite a lot. And this is not something I have investigated in this project, or it's not something that is very possible with this current setup. In comparison with a high power system, this is a much more safe and low power solution, which makes it a suitable candidate for research and education purposes, or when we want to deploy a setup on hardware, but kind of wants to see whether the simulation setups is actually valid. But the fact that it is low power also means that we need to make some tweaks before moving on to a high power. Of the 3 future works that I've mentioned on this slide, I think the most important future work here is a small signal stability analysis, because at the moment I can't control the currents of the grid following inverter to 0 when both inverters are operating in closed loop, which shows that there might likely be some sort of an unstable node. So if I were able to model the current controller as a circuit impedance in series with the inductor and the voltage controller as a impedance like in parallel with the capacitor voltage, then we would be able to get a holistic picture of both the power, the influence of the filter, as well as the controller itself on the stability of the system. And in that way, we could analyze some of the unstable nodes and make this a much more robust solution. So thank you so much for listening to my presentation. And before I end this, I'd like to show you a very brief video for my demo.